So let's go ahead and get started. So let's see. So in the first example of the last lesson, we found, so let me just write all of this out. Okay, in the first example of lesson 20, we found the max and the min, and you know what? Let me not call them max and min. Let me call them extrema. Okay, we found the extrema values of f of xy, and if you recall, that function was equal to x times y, excuse me, subject to the constraint that the point xy must also satisfy this function g of xy, which was x squared over 8 plus y squared over 2 equals 1. So we were maximizing or minimizing this function subject to the constraint that the x's and y's that actually go into this to maximize it and minimize it also happen to lie on this ellipse. That's what we were doing. Okay. Equals 1. Okay, now we found 4 points that satisfied. Okay, we had the point 2, 1, 2, minus 1, minus 2, 1, and minus 2, minus 1. Okay, and the respective f values, in other words, when we put these points into xy, the respective f values, I'm going to just write them underneath. We had 2, minus 2, minus 2, and 2. So these two were the points where the function achieved a maximum, and these two were the points where it achieved a minimum. So let's take a look at what this looks like geometrically. Excuse me. So let's look at this geometrically. Okay, so what you have, I'm going to draw a little xy plane here. And again, we're looking for points xy in the xy plane that actually maximize this function xy, but that also happen to lie on the ellipse. Well, xy, if you do the level curves of xy, in other words, xy equals some constant, xy equals 3, xy equals 2, xy equals 5 halves, whatever, you're going to get a series of hyperbolas. That's what you're going to end up getting. So I'm going to go ahead and draw a few, but first we want to make sure that x and y actually satisfy this equation. In other words, that they lie on this ellipse. So let me just go ahead and draw an ellipse here. I'm not very good at drawing ellipses, but again, the drawing itself is not that important. So this is x squared plus y squared equals 2, where you have this right here is the distance from the center to this vertex is going to be radical 8, and this one is going to be radical 2. So the points xy that lie on here, which ones are the ones that actually maximize? Well, we found these points right here. So 2, 1, there was 1, negative 2, 1, negative 2, negative 1, and 2, negative 1. Well, here's actually what it looks like geometrically. Oops, it's not very good. Let's make it a little bit better than that. That's that. So there's another point. So in other words, if you were to look at this, at the point 2, 1, negative 2, 1, negative 2, negative 1, and 2, negative 1, these are the points that maximize the function. These are also the points that happen to lie on this ellipse. So the constraint is satisfied. Those are the points that we found. Well, geometrically what it is, take a look at this. As it turns out, at this point, if I were to actually take the tangent line to both curves, as it turns out, they correspond. In other words, if I were to take the this tangent line at this point happens to be the same for this curve, G, and for this curve, F. So what ends up happening is the following. The gradient at those points looks like this. The gradient of F will be this way. The gradient of G will be this way. Because the tangent lines correspond, the gradient vector is perpendicular to the tangent line. So as it turns out, they're moving in the same direction. Well, one is going to be either the same length or is going to be longer than the other. And that's what the Lagrange multiplier is. It's just a scalar multiple of the gradient vector. So when we say that the gradient of F equals some multiplier lambda times the gradient of G, what we're saying is they're either moving in the same direction or in the opposite direction, depending on whether lambda is positive or negative. In other words, the gradient vector of G, or the gradient vector of F, is a scalar multiple of the gradient vector of G. The gradient vector here looks something like this. Here, so this was the max and this was a max. Notice the gradient vectors are in the same direction. In the case of the mins, the gradient vectors are actually pointing in opposite directions, but it's still just a scalar multiple of the other. In other words, they have the same direction, either this way or this way, but they're part of the same line. And they're on the same line because the tangent plane, or the tangent line itself, to the curves at that point that satisfies the max and min, they are the same for both curves. So the gradients are multiples of each other. The gradient vectors are multiples of each other. And that's what's happening. That's what this actually says. So I just wanted to demonstrate geometrically what it is that's actually going on. And again, it's a good idea to sort of see that, to get an idea of where it comes from. But again, it's the algebra that matters, because when you move on to higher dimensions, you're not going to quite have the geometric intuition that you can get. For example, this works in 2 dimensions. If we were working with a 3-dimensional example, a function of 3 variables, we'd have x, y, and z. Then we'd be talking about surfaces, where you have one surface and another surface. The point P that happens to be an extremum is going to be the point where those 2 surfaces actually end up touching, and the tangent plane to those surfaces is going to be the same. So the gradient vector is going to be perpendicular to that tangent plane, and the gradient vector, they're either going to be in the same direction or they're going to be in opposite directions, but they're going to lie along the same line. Okay, so that's it. That's all I wanted to demonstrate. We're going to do one last example for Lagrange